Think about the most fundamental law of our universe. No, it's not gravity nor the speed of light. It's a deeper, almost sacred rule. Information can never be destroyed. Every atom, every particle carries a history. You can burn a book, but in theory, you could reconstruct every word from the smoke and ashes. Information just transforms until we get to a black hole. These cosmic monsters don't just swallow stars. They threaten to erase the very memory of the universe, violating our most sacred law. And the man who showed us this was the same one who tried to save us from the paradox he created, Stephen Hawking. Today, we dive into the greatest war in modern physics, where reality comes undone. To understand this crisis, you need to know the two titans of physics. On one side, we have Albert Einstein's masterpiece, general relativity. It's the theory that describes gravity as the curvature of space-time and gave us black holes, these gravitational wells from which nothing escapes. According to relativity, black holes are shockingly simple. They don't care about the details. Throw a million encyclopedias or a million rabbits into one, and the result is the same. The black hole only remembers three things: its mass, its rotation, and its electric charge. All the complexity, all the rich information about what fell inside, the color, the texture, the history of each particle, is seemingly lost forever. It's locked behind the event horizon, the point of no return, incommunicable with the rest of the universe. This is known as the no-hair theorem. It states that black holes have no hair, meaning they have no external features that reveal what's inside. For general relativity, information is effectively erased from our observable universe. This idea was already deeply unsettling to physicists like Jacob Bekenstein, even before Hawking. Bekenstein argued that if a black hole swallows something with entropy, a measure of disorder and information, the total entropy of the universe cannot decrease. He proposed that a black hole's entropy, its capacity to store information, should be proportional to the area of its event horizon. This would make black holes the densest and most efficient information vaults in the entire cosmos, suggesting that the information wasn't truly lost, but rather encoded in a way that defied our understanding. On the other side of the battlefield, we have quantum mechanics. It governs the strange and wonderful world of particles. And its most fundamental law, called unitarity, is an elegant way of saying that information is eternal. It can be scrambled, but never, ever erased from existence. Quantum mechanics insists that if you know the final state of a system, you can, in principle, reconstruct its initial state. The information about a particle's past is always encoded in its present. It's a conservation law as fundamental as that of energy. Until, in 1974, Stephen Hawking decided to force a meeting between these two titans in the most extreme place in the universe, the edge of a black hole. And in doing so, he inadvertently started a war that would shake the very foundations of reality. Hawking made a discovery that changed everything. He realized that due to quantum effects, black holes are not completely black. They are not eternal prisons. They glow. They emit a thermal radiation, now known as Hawking radiation. To understand this, imagine the vacuum of space not as nothingness, but as a bubbling sea of virtual particles. Pairs of particles and antiparticles that pop out of nothing and almost instantly annihilate each other, returning their energy to the vacuum. This happens everywhere, all the time. Now imagine one of these pairs appearing right at the edge of a black hole at the event horizon. Before they can annihilate each other, the extreme gravity can pull the pair apart. One particle falls into the black hole, while the other escapes into the universe. To a distant observer, like us, it looks as if the black hole has just spit out a particle. This escaping particle has positive energy, and to conserve total energy, the particle that fell in must have negative energy. This means it effectively reduces the mass of the black hole. And here is the time bomb. This constant emission of particles causes the black hole to lose mass. Very, very slowly, over cosmic eons, a black hole evaporates. It shrinks, gets hotter and hotter, and finally disappears in a final flash of radiation. A black hole's temperature is inversely proportional to its mass, which leads to a truly bizarre fate. A black hole with the mass of our sun is incredibly cold, with a temperature of just 60 nanokelvins, far colder than the universe itself. but as it loses mass, it heats up. This heating accelerates the evaporation, which heats it up even more, creating a runaway cycle. In its final moments, a black hole the size of a mountain would have a temperature of trillions of degrees, exploding with the energy of millions of nuclear bombs. The timescale is unimaginable. A black hole with the mass of our sun would take longer to evaporate than the current age of the universe. But fundamentally, it is not eternal. The vault that held all the information that fell into it one day ceases to exist. And here is the crucial point, the heart of the problem. Hawking radiation, according to the original calculations, is purely thermal. This means it is completely random. The particles that escape carry no information about what formed the black hole. Do you see the crisis now? The cosmic crime? If the black hole completely evaporates and the radiation it leaves behind is random and contains no information, then all the history, all the unique identity of what fell inside, has been permanently erased from reality. This is a direct violation of the most sacred law of quantum mechanics. General relativity says information is lost behind the event horizon. Quantum mechanics says information can never be lost. Hawking radiation says the vault that held the information disappears. This is the information paradox. It is a fundamental contradiction in the laws of the universe. One of our most precious theories, relativity or quantum mechanics, has to be wrong in its current form. The universe is screaming at us that we are missing something big, something profound. So, where does the information go? Physicists have been wrestling with this for almost 50 years. Some, like Leonard Susskind, propose the holographic principle. Perhaps the information doesn't actually fall into the black hole, but gets encoded on its surface. This idea is much deeper than it sounds. The holographic principle, which emerges from string theory, suggests that the entire three-dimensional reality we perceive might actually be a projection of information stored on a distant two-dimensional surface, like a cosmic hologram. The black hole would just be the most extreme example of this principle. If this is true, it means that space-time as we know it is an illusion, an emergent construction from more fundamental quantum information. Solving the paradox, in this case, not only saves the laws of physics, but completely redefines what we understand as reality. Another possibility is that the information is, in fact, hidden in the Hawking radiation. Not in an obvious way, but in extremely subtle quantum correlations between the emitted particles. The radiation only seems random. If we could collect every single particle emitted over the black hole's lifetime, we could, in theory, decipher the message. Hawking himself, later in his life, proposed a solution. He suggested that black holes might have quantum hair, subtle fluctuations in the gravitational field at their event horizon. These fluctuations could carry the information out, resolving the very paradox he created. The truth is, we don't know. But the search for this answer is the quest for quantum gravity, the theory of everything. Solving the information paradox isn't just about understanding black holes. It's about understanding the fundamental nature of space, time, and reality itself. It's about discovering if the universe keeps a record of everything that has ever existed, or if it allows entire chapters of its history to be simply erased. The information paradox shows us that the greatest mysteries aren't just in distant galaxies, but in the very laws that weave the fabric of the cosmos. And if you think that's mind-blowing, just wait until we explore what might have existed before the Big Bang. To continue this journey into the unknown, make sure to subscribe and turn on notifications. The universe is full of secrets, and we're just beginning to scratch the surface.